Hello and good morning. We are from Group 8. We'll be presenting about a converging diverging nozzle throughout this video. This project will focus on analyzing the flow through a converging diverging nozzle by using a CFD-based approach. The goal is to understand how nozzle influence the fluid behavior, especially under high-speed condition. By applying this fundamental principle in compressible flow, we aim to simulate and observe the key flow characteristic. Here, let's talk about the objective, which is to model and simulate the supersonic airflow, analyze the effect of nozzle pressure ratio on shock formation and fluid behavior, compare the theoretical value with the experimental result for validation purpose, and finally, to visualize the variation in temperature, pressure, density, and velocity distribution along the nozzle. So let's dive into it. Moving on to the theoretical background. To understand how CD nozzle work in supersonic condition, a compressible flow theory is required. As air flows through the narrow section of the nozzle, it will speed up and reach the highest speed at the throat, and then will further accelerate at the wider section of the nozzle if the pressure ratio is high enough, around 7.82. A significant change in pressure and temperature occur during the shock wave, which is crucial part for supersonic flow that can be described by Navier-Stokes equation along with the continuity and energy equation.
Okay, let's go to the literature review. So, what's the journal we got? Okay, from the Share Afghan Khan ET AL 2021, which conducted a computational flow dynamic CFD analysis using ANSYS fluid to examine the compressible flow through a two-dimensional converging diverging CD nozzle. So from their study, which aligned closely with the goals of this project. So it really demonstrates the application of fluid kinematics and conservation equation in CFD modeling for high-speed compressible flow. They emphasize the importance of accurately simulating shock wave behavior and flow acceleration in supersonic regime. The study used the compressible flow form of the Navier-Stokes equation. So, along with the continuity and energy equation, they employ a density-based solver ideal for high Mach number flow. To model turbulence, the K epsilon model was used, which balanced efficiency and accuracy in capturing shock wave generation and flow separation. The result actually showed the flow of characteristics, including the shock pattern and velocity profile, were consistent with theoretical prediction, further validating the importance of the shock trends and flow separation control in supersonic nozzle application. Yes, all. Okay, next for the nozzle design, which the design and the analysis in this study involve a symmetric 2D converging diverging nozzle. So engineered to operate at Mach 2.0 at the throat. So the nozzle function is to accelerate subsonic flow at the inlet to supersonic speed at the exit. So utilizing the principle of the compressible flow, the smooth transition from the subsonic to sonic speed at the throat result in supersonic flow beyond the throat. So the nozzle geometry, it consists of dimension as shown in the figure. Okay, this nozzle is designed with the goal of achieving a nozzle pressure ratio (NPR) of 6, 7.82 and 8.2, which is essential for proper expansion. So this variation of NPR lead to either under expanded or over expanded flow, which result in different shock pattern and flow characteristic downstream of the throat. So the geometric dimension and flow parameter are chosen to ensure smooth expansion and to minimize shock-related flow separation.
Okay, so now I will explain the methodology part of our simulation. Meshing is a critical step in CFD modeling, especially for compressible and high-speed flows. This shows the initial 2D geometry of our nozzle, including the converging section, throat, diverging section, and the extended duct. The geometry was divided into segments to allow local mesh refinements in areas where large change in flow properties are expected. The quadrilateral dominant method was first applied for meshing. After preparing the geometry, we defined the boundary conditions by assigning name selections as shown. The inlet, outlet, and wall regions were labeled to apply the correct flow constraint in ANSYS fluid. Edge sizing was applied to 8 edges, with the number of divisions set to 20 and no bias type. This provided uniform mesh spacing for general regions. Next, this shows the default unstructured mesh generated by ANSYS. This mesh uses irregular triangular elements and is quick to create, but it is not suitable for resolving sharp gradients or shock waves in compressible flow. In this version, edge sizing was applied to 4 edges with a number of divisions equal to 40 to target moderately important flow regions. So as shown, to increase accuracy, the mesh was improved using fast meshing. Here, the mesh was refined mainly at the throat and diverging sections with 30 divisions assigned along 6 edges. This higher density helps capture shock waves and flow expansion more accurately while reducing numerical errors. So this shows the final mesh density for the outlet region. The number of divisions was set to 250 along 4 edges of the long outlet wall. This fine mesh allows detailed resolution of supersonic flow features downstream of the throat, which is critical for capturing flow behavior correctly. So overall, the edge sizing was carefully adjusted to balance accuracy with computational cost. Here, map face meshing was applied to all 7 rectangular faces, and quadrilateral elements were used throughout the domain. The simulation was run using the density-based implicit solver for compressible flow, with standard initialization from the inlet, a current number of 5 and a total of 1000 iterations. The residuals for continuity, momentum and energy all dropped below 10 to the power of -4, which confirms that the solution converged properly and the mesh setup was stable.
Okay, now I will show the fluent setup that we have used for the simulation. Start up NC's Fluent and choose steady and density based solver. Turn on energy equation and set K epsilon as the viscous model. Then set the material as ideal gas with the given properties. Then set your pressure and temperature for inlet and outlet according to your NPR value. Use standard initialization and initialize the solution from inlet and run calculation for 1000 iterations.
Now, let's look at the result and discussion from our CVD simulation of compressible flow through a converging diverging nozzle. We use NC's Fluent to observe how pressure, velocity, temperature and density change as the fluid accelerates from subsonic to supersonic speeds. First, the contour plot shows the expected behavior. Pressure is the highest at the inlet and drops significantly at the throat, confirming low acceleration. Velocity increased rapidly after the throat and peak at the exits. Temperature and density both decrease along the nozzle with the expansion and acceleration. Next, we extract value at the key point. At the inlet, temperature is about 300 Kelvin. Velocity is 49.4 meter per second and density is 9.16 kg per meter cube. At the exit, velocity rises to 242 meter per second, while temperature and density drop to 241 Kelvin and 3.06 kg per meter cube, respectively. To strengthen the analysis, we generate XY plot of each flow variable along the nozzle. Velocity position show sharp acceleration after the throat. Pressure drop steadily while the steepest fall near the throat. Temperature and density decrease continuously, consistent with supersonic flow. This result match the theory well, and the absence of shock wave indicates that the nozzle operates close to the design NPR of 7.82. Finally, all errors were under 30%, which confirm our simulation setup was accurate and reliable for analyzing compressible flow. That's all from me. Thank you.
So in conclusion, our simulation of the converging diverging nozzle worked as expected. As the flow passed through the nozzle, velocity increased after the throat while pressure, temperature and density decreased. These results match the behavior of compressible flow in a properly designed nozzle. We also didn't observe any shock waves, which suggests the nozzle design was efficient, especially with a pressure ratio of about 7.82. When we compared the simulation results to the reference data, the percentage error for the maximum values of the pressure, temperature, velocity and density was all below 30%. This shows that our setup was accurate and reliable for analyzing compressible flow throughout the nozzle.